Now, let me start this lecture, which is aimed to give you some introduction to the dynamics of the Earth system. And the dynamics means also to give you an overview of the processes that are involved, the physical and not only physical, chemical, and other kind of biophysical processes that govern the interaction of the several systems that altogether form the so-called Earth system. What is the Earth system? The Earth system is the totality of the processes, includes the totality of the processes that govern the dynamics of the Earth, where when we say Earth, we mean not only the inner Earth and the land surface, but also the atmosphere. Usually we talk about Earth system indeed as the whole of Earth plus atmosphere, and we talk about instead the planetary system when we talk about the totality of the system, including the different planets. Usually there is a branch that is called Earth and Space Sciences that includes both the study of the sciences of the Earth system and the planetary systems. Usually they are analyzed and to some extent modeled together as a unique entity, because understanding how the dynamics of the other planets evolves gives us the opportunity to better understand, to gain indication on the future evolution of the Earth, because there are other planets that are older and they have a similar evolution as the Earth, of course with different temperatures, different situations, but the evolution presents a lot of similarities. And therefore, why do we study Mars, for instance? We are interested in the history and the past history of Mars, because this allows us to make predictions on what could be the future evolution of the Earth system. To give you an example, there were and still are a lot of researches dedicated on finding water over Mars. And keep in mind that up to 20 years ago, it was still a question mark. Is there water over Mars? And now we know that indeed there is water. There has been a lot of water, and therefore understanding why this huge amount of water that was over Mars, included in the Mars Earth system, now it's reduced a lot, gives us a way to better understand what could be the future evolution of the Earth. There are, to give you some more details, several possible explanations for the massive reduction in the volume of water in the Mars system, and the most credited interpretation is that there has been a scission of the molecules of water, and therefore the split between the atoms of hydrogen and oxygen, and it seems that this split has been favored by direct exposure to the solar radiation without the filter of the atmosphere, which was once in Mars, included over Mars, but then it looks like, this is one of the interpretations, that the atmosphere disappeared once the magnetic system of Mars cheesed, the magnetic field of Mars cheesed. And it cheesed because the progressive cooling of the planet has slowed down the circulation of iron material in the inner core. So we know, for instance, today that the magnetic systems of the Earth is originated by the movement of iron in the inner core, and therefore it's plausible to hypothesize that in the future evolution of the Earth system, it may happen the same, a progressive slowdown of the magnetic field, which may cause disappear of the atmosphere. Why? Because it seems like the magnetic field is like a screen against the solar radiation. So once that the magnetic field is annihilated, disappears, it seems that it's highly likely that the direct solar radiation is not screened anymore, and therefore causes the disappear of the atmosphere and subsequently the split of the water molecules. The volume of water that we assume was present on Mars was indeed huge, and much more than the volume of water over the Earth. How did we understand that? From the analysis of the geography of the planet. And so we can see valleys by looking at the depth of these valleys, the dimension, and the size of what we assume have been lakes, based on the topography. We can estimate an amount of water that was indeed very large. What we cannot know, what we still don't know, is if the atmosphere of Mars was livable or not. And because it may be that, even if there is atmosphere, still there is some atmosphere on Mars, and the current atmosphere is not really livable. And therefore, it's not clear whether in the past it was different. There was a different situation. Okay, so the Earth system. First of all, it is an interrelated system. So when there are interrelations between several processes, we say that it's a complex system. And, complex system, why? Because indeed, it's not easy to define complexity in science. You don't find a unique definition. And usually, complexity is defined by giving examples. For instance, one example is there is complexity because there are several systems interacting. And what are these systems? There is what we call the climate system, and then there is what we call the ocean system. There is what we call the life system, and there is what we call the societal system and the economic system. These systems are interacting. What does it mean? That there are links connecting one to the other, and these links can originate a two-way interaction. So it means that society may affect, for instance, the ocean system, and the ocean system, of course, affects society, but it's not a one-way interaction. Of course, for instance, climate affects us, but it's also the humanity affecting climate, as we know. And therefore, these interactions, two-way interactions, which may give rise to possible tipping points, and we already discussed about them. It's one of the definition of complexity, but it's not really a definition, it's an example. Like, it is complex because there are several interactions. But how can we define complexity? It is something that, as I said, there is not a unique agreement among scientists, but I like to focus on a definition which it's not formally expressed. And this definition, I like to define complexity as a feature of a system that implies limited predictability. And this is something that I really like as a definition. I think it is a possible definition. So you have a system and ask yourself the question, can I predict the system in the future with certainty? And if the answer is to a limited extent, typically to a limited time horizon, this means that there is complexity. And I give you another example. If you drop a body in the void, and you are in the void, you can make a prediction of its position, and you know the gravity force with certainty. Okay, so there is no uncertain definition of gravity. Then you can write an equation that describes the position of the body falling in the void forever. So if the void is extended forever, you can make a prediction where the body will be in 1 year from now. This means that there is no complexity because you can make a prediction. And instead, if the answer is like, yes, we can predict the position of the body, but it's not in the void, it's in the air. So you can make a prediction, but actually this prediction is extended to a limited time horizon. It's not a limited time horizon. Why? Because you don't know what is the density of the air after maybe 10 meters of fall. This means that you can make a prediction until you know the density of the air. But if after a certain distance you cannot know the density of the air with precision, and moreover, let me also say, it's impossible to know the density of the air with precision, because whatever you take a measurement, you should take a measurement every micron, not even every millimeter, because otherwise there is a gap in the measurement. So given that you cannot make this definition of the exact density of the air, it means that your prediction is reliable for some meters of fall, but not it's not infinite reliability. And therefore, this is a sign of complexity. Okay? This definition may, in a way, not include the case of perfect randomness. Perfect randomness means unpredictability, but on the other hand, perfect randomness is an example of no complexity. Okay, so basically, I'm saying that this definition that I am providing is not comprehensive, is not comprehending, including fully random processes. And but fully random processes are an example of, anyway, no complexity, because I mean, when I toss a coin, there is no complexity, because it's very clear I cannot make any prediction and there is no complexity. Okay, but this is more of a philosophical discussion. What is the implication for us when we talk about the Earth system? The Earth system is complex. This is agreed by everybody. This means that a deterministic description is a fully deterministic prediction, a fully deterministic prediction is not possible. And therefore, when we build models, we have to take into account that there is this potential limitation. I tell you, this interpretation, some people who are really deterministic in their way of thinking don't agree. They say, look, if I was able to make a very precise measurement of everything, I could build a system model that is perfect, deterministic and perfect. But on the other hand, my reply is that we cannot really define input variables. We cannot really take a very precise measurement of the geometry, of the trajectory, of the dynamic trajectory of any entity that is evolving in the Earth system. So given that even with the progress of remote sensing, the progress of monitoring techniques, even that still we cannot get a very precise definition of what we call control volume, which means the space that we want to describe, then, I mean, there is a limitation in our capability to predict. And this is an important starting point, in my opinion, because it tells us that, for instance, climate models cannot be perfect in their prediction. And this is something that in engineering has a strong implication. So the system then identifies, and this is a formal definition, the unified whole resulting from the aggregation of interrelated entities that are relevant to the dynamic evolution of the planet Earth and its atmosphere. Okay. The Earth system is closed. It means that only energy can flow in and out, with the only exception of meteorites, mass forces, masses that can enter from the space. But I mean, this is really a very tiny exception. Okay, so that system, we assume it's closed. Only energy can flow in and out. And what are the entities that are cited here? Entities include the dynamic processes that connect the different parts of the system itself. So this is a modern view of the system, because keep in mind that in traditional sciences, we split the scientific understanding, the scientific investigation in disciplines. And so we split between physics, chemistry, and engineering, which I like to classify as a science, and And in our analysis of the Earth system, we split between atmosphere and surface water, groundwater. This is a classic view. And this classic view today is a bit criticized because people say we have to be interdisciplinary. Why we have to be interdisciplinary? Because what we need is what is called a holistic view. Holistic is a bad word, but it just means consider the system as a unique entity and not splitting between disciplines. Because these people say, and this is correct, that if you only focus on a subsystem, on the climate, you don't fully understand the connections between one system and another one. And if you don't understand the connections in turn, you cannot be precise in modeling the system. So if you focus on the climate system and you don't consider the connection with the societal system, then of course you can get the CO2 emissions as an input, an external variable. But still, there is a limited comprehension of the intimate relationship between climate and humans. So basically, what we aim to do today is to take this holistic approach. On the other hand, let's also say that the disciplinary approach has still some advantages because it allows to build models that are more simplified. So what is the criticism against the interdisciplinarity, against the holistic view? Is that the model becomes too complicated, too many parameters, and too many parameters means a lot of uncertainty. And this is what very often I point out, like, okay, that's fine. The idea of connecting humans with the climate is fine, but on the other hand, what about uncertainty? Does it become unmanageable, or still it is manageable? And therefore, it's important to keep in mind what are the differences and what are the pros and cons of the two approaches. I still believe that sometimes we need to focus on a very limited portion of the system. So if we want to solve the flood problem in the city of Faenza, I think that we need really to focus on a limited control volume, which is the river and the surrounding areas, and then build a very detailed, but at the same time simple model of that part of the system. Of course, in doing that, we don't have to forget feedbacks, links between the societal links with the economic system, societal system. So basically, if we believe, to talk in engineering words, that a solution is needed, we don't have to forget the implications in economic terms, and economics, I mean economics, so not economical term, not only money, but the whole context of the economic system, the implication of the solution. So basically, and poorly speaking, does the community have the money to make it or not? Because this is a very trivial example of a connection that cannot be ignored. And when you read papers, sometimes keep in mind that pure scientists may have like the temptation of focusing on a very limited problem and forgetting what are the implications, so the side effects. And this comes from ignoring these connections. So we should be flexible enough in order to understand what is the approach that we are taking and evaluate the limitations and also evaluate the alternatives. And this, in order to get this flexibility, knowledge, of course, is important. So what is the traditional approach then? I said, we split in different subsystems. Let's mention the main one. And this traditional approach is also called reductionist. You know why, but it's important that you know the term, because sometimes in scientific debates or papers, you see, we take a reductionist approach. This is the meaning. Like, okay, I focus only on a limited portion of the control volume, not on the whole Earth system. Also in climate modeling, sometimes they try to work on global models, but sometimes they decide to focus on the climatic evolution of a very tiny portion of the land surface. Why? Because this allows them to get a final resolution. Okay, so what are these subsystems? These subsystems are traditionally called spheres. Spheres meaning subsystem of the Earth system. So we talk about the atmosphere, and now we understand why atmosphere, okay? Because it's a sphere of the Earth system. But then there is the geosphere, which is the sphere including the Earth's surface, okay, and the processes that take place in the Earth's surface. Probably geosphere also includes the processes of the deep Earth. And we should look at the definition. The biosphere means the sphere of the living systems, and the hydrosphere, which is the water sphere. Okay, and you see that there is some intersection, because when we talk about the hydrosphere, it's not only liquid water, it's also water in a vapor form, and therefore includes part of the atmosphere. There are intersections, and you see already a possible problem of the reductionist approach. And sometimes we talk about the ocean system, okay, that's fine, but indeed the ocean system is extended also for a limited extent into the land, because ocean water is infiltrating into the land, and therefore sometimes you cannot really draw a boundary between the ocean system and the land surface, the geosphere, because the boundary is a bit changing, not only because of the changing sea level, but also because there is some water from the ocean that gets into the earth, and not only water from getting into the land, not only water from the land into the ocean. And there is, in my web pages here, here. Oh, this is the PowerPoint, just a second. This is here, sorry. In my web page, there is in this lecture, because of course now I'm looking at the PowerPoint lecture, PowerPoint version, but here is the extended one. And here there is the link, geoscience videos. These videos are dissemination videos, which talk about the Earth system and several of its parts. These are not scientific videos, are dissemination. So they are trivial, but they are short and they are quite a nice reading, which I suggest you to take a look. It may be interesting to get. There are to get some information, and there are some which I think the Earth system is the one I am referring to, but it's not clickable, so I'm looking for an index. Let me see. Okay. Continental drift, the Earth system. Let me see. Yeah, it is the Earth system. This one is talking about the spheres. We are not watching it now, but there is also something on climate, which let me see. There is one, maybe. Okay, if you browse it, there are a couple of links on glaciations, past videos on past glaciation, and one on climate change, which are nice. Can't find it, but if you look in Google geoscience videos, climate change, you find it. Okay, let me close this. Okay, perfect. So, presentation. Other spheres often considered to be relatively minor importance. The cryosphere is the sphere of snow and ice, lithosphere and pedosphere, soils, and technosphere, this is humans. Okay, so we talk about the social system, socioeconomic system, and we can also call it the technosphere. Okay, now what are the connections among spheres? We said that it's important to look at the connections. So how can we look at them? It's an interesting approach is to look at flows of matter between the several components of the Earth system. So exchange of matters. This is a nice way of looking at the interactions. For instance, we may look at the carbon cycle. The carbon cycle describes the flow of carbon among the different spheres. And we know that the carbon cycle today is very popular. There is really a massive research on the carbon cycle. And the attempt is to describe the fluxes, precisely, the fluxes of carbon between the different spheres and to try to split among the different causes. So, for instance, you know how much is important to determine the mass of carbon that is released by human activities and compare it with the mass of carbon that is released by the oceans. And there is still a lot of uncertainty in these assessments. You can understand why it cannot be measured. We can measure the CO2 concentration in the atmosphere, but understanding whether the CO2 concentration increases, so attributing the delta, the difference in carbon concentration to human activity rather than human activity in terms of like transportation, rather than a decrease in the extension of the forested areas, rather than an increase of the temperature of the ocean, which of course can be related to human activity as well, but in a direct way, it's a problem. It's still a gigantic problem. There are several billions of euros that are invested every year in the only European community to try to understand, to build models of these exchanges. And we may look at a sketch. This is one possible sketch of the carbon cycle, which, I mean, every cycle, any exchange of matter, remember, any dynamic evolution of the Earth system takes place because there is energy. Energy moves these flows. To move these flows, you need energy. And what is the energy source for the Earth system? Is solar radiation. And it's the only flow that can get into the Earth system because otherwise it is closed. Okay? And so even, I mean, CO2, carbon, is not increasing during these exchanges. It may increase in one part of the Earth system, atmosphere, because there is a decrease, there is a flux of carbon from another part. So in the past, what happened is that there was a huge carbon storage through fossil fuels. And fossil fuels originated by degradation of vegetal material that then was embedded into the soil. You know the reason why, because of the evolution of the Earth. And these underground deposits of gases and fuels are huge deposits of carbon. Of course, for instance, when we burn fossil fuels, we generate a transfer of carbon from one part of the Earth system, what we call the geosphere, to another part of the Earth system, which is the atmosphere. But there is no global increase. This is why some people think that a possible solution to climate change may be geoengineering. What is geoengineering? It includes several types of applications, but one application of geoengineering is injection of carbon in the underground, for instance, by using the wells that we previously used to extract the oil. Therefore, a well is exhausted. The idea is I re-inject back the carbon from the atmosphere. This is one possible solution. It's a man-made flow which shows perfectly the possible interaction between the human system and the possible effect of the human system on the carbon cycle. By the way, this solution still has some open questions, like it's not clear if this carbon that is injected back is really stored there, because there are fractions, so it's carbon it's a gas, and therefore can leak through the fractures and can get back to the atmosphere. And it's also very costly. So basically, but I think it is a nice example. And here you can see what are the several different exchanges. There are exchanges by human, industry, transportation. There is carbon stored in the ocean and the microbial community, but also dissolved into the ocean, and this leads to ocean acidification. And then there is the vegetation, the growing vegetation. Even when we burn woods, we generate a transfer of carbon, and it's also massive from the vegetation, stored in the vegetation to the atmosphere. And by looking at these links, it's a way to focus on, by looking at these fluxes, is a way to focus over the links connecting the different spheres of the Earth system. And it's a nice way of doing that, because this really allows us also to quantify fluxes that are very relevant to our understanding and to our purposes. Your question.
Is this possible to become again? You mean to become an oil or oil and natural carbon? There is that carbon, natural carbon that is used to produce energy that they extract as natural resource.
Yeah, but I think natural carbon is still emitting CO2. So I'm not an expert on that, by the way. But okay, let me focus on your question. When you inject carbon into the underground, the idea is that in the long term, you are accelerating something that may happen in the long term, that happened in the long term in the past. So the idea is maybe that in the underground it becomes organic, or it becomes natural carbon. This is still not clear. I mean, it's not proved that this is the doubt.
It takes millions of years.
It can take a millennia, but it may also, because it's a different process. I mean, the original oil originated by vegetation, so it was dead trees that in the Martians they long time transformed, and then they got into the underground for several different processes, tectonics or whatever. And here it's a different story, because we are not injecting fluids. We are, in a way, injecting gases, and also you put this gas in the underground directly, not in the long term that required to tectonics to put it at a huge depth. So it's not clear if we will be able to reproduce it, and there might be some leakage before the transformation is completed. And because they made also some experiment to measure the CO2 concentration in the surroundings. And there was not final conclusion, but it is indeed the huge feeling, the huge concern that it may leak. And the other comment that you made at the start, it's not relevant to the question. Like natural carbon, I think, is not like methane. It's still emitting a lot of CO2. Instead, the natural gas, sorry, not methane, the natural gas, indeed, this emits much less concentrations of CO2. But I'm not an expert in this. I would like to make it clear. I'm also not an expert in the modeling of the carbon cycle. I mean, I hope I am an expert in the modeling of the water cycle, which is another way of looking at the links. But for the carbon cycle, I reviewed a lot of papers about that, but my review is just given from the perspective of a not expert. Because when you submit a paper or a research proposal, sometimes they want to get the opinion of non-experts, because it's a way to check if the paper is interesting to a wide audience. So I am often asked to review papers and proposals on the carbon cycle, but my opinion is regarding the opinion of a non-expert, and I fully agree with that because I'm not an expert. But still, I can recognize if something is reasonable or not, because of course, I know the scientific method, and therefore I can check whether what is written there follows an accepted scientific method. This is the water cycle that I mentioned. Is another way to look at the exchanges between the different spheres. You know a lot about the water cycle, so I'm not giving details on it. What I would like to say once again is that even if it looks very simple, indeed it is not complicated, because the water cycle is a physical process. So the laws of physics governing the water cycle are very simple. It's conservation of mass and conservation of momentum. That's it. And conservation of momentum allows you to model the dynamics, so the flows. And conservation of mass is the additional constraint that comes from the fact that the system is closed, so you have conservation of mass. And therefore, it is very simple, indeed, also to describe it. So, but indeed it is complex. Why? Because these processes, they are strongly dishomogeneous. They are not homogeneous processes. Homogeneous means that if you move in the space, there are changes of everything, and in the three directions. And therefore, you need a 3D model, 3 dimensions, and the 3D model is not really a big problem. With the modern computational facilities, you can really deal with a 3D model. The problem is given by the description of the geometry, because, I mean, these fluxes, if you want to describe a flow, you have to describe the pipe, or let's say, you have to describe the geometry of the media along which you observe the flow. And this geometry, you have to describe it in 3D. And unfortunately, strong heterogeneity means also heterogeneity in the media. Now, media means the porous media, for instance, in the underground, but also in the atmosphere. It's strongly heterogeneous. And therefore, you have to make measurements in 3 dimensions. And these measurements should be done at the microscopic scale. But with microscopic, again, I mean something really microscopic, something that you can't see. So if you can't see it, you understand, it's impossible to survey it unless you use very sophisticated, like microscopes, materials, and techniques that you can really use. So what is the solution? The solution is very simple and very smart. The solution is I average over a finite size of space, over a finite volume. So from the microscopic scale, I turn it to the macro scale. Even if you average over a volume of 1 cubic centimeter, you already left the micro scale. You are already in the macro scale. But in doing this average, what you describe in terms of variables, what your model describes is the average. So if I average over this table the air density, my resulting measurement of air density is the average over this table. And the average means statistics. Remember, it means that you are computing something that is statistical, which means uncertainty, because the average is not over this table. It's not anywhere here, the average. It is representative, but there is variability. So it's an approximation. It's already statistics, which means, again, uncertainty, which means, again, complexity, which means, again, limited predictability. So this is one thing that I really want to say of the water cycle. It's very simple, but sometimes we cannot describe it. And there is also one more thing that I would like to say. The fact that we cannot really see it and think of the underground means that there are some fluxes that we don't see. It means that there are some fluxes that we don't understand. And I give you a very practical example. We have only recently discovered, like 20 years ago, that in many floods, the water that floods you is not the water that came from the rain, it's old water. It was like stored in the Earth system. And then when you get the forcing of rainfall, this water that was quiet, stored, then gets moving. And what floods you is old water. We only discovered recently this. How did we discover it? By studying the isotopes. So you go to the river, you take a sample and you measure the isotopes, and you can connect these isotopes to past rainfall. And we see that the water that is in the river rained 1 year ago, not yesterday. This is an example. Another example is that we still don't understand when it rains where the water flows, because if you look at the river, it's clear there is water flowing, there is a flood. But if you look over the isthmus, unless an isthmus is really impervious, it means no permeability, okay, you see the water. Sometimes it happens, you go over the roof of these houses during the rain, you see the water flowing. But if you go over a natural isthmus, you don't see the water flowing over the ground. So it must flow in the underground. But we still don't know if it is very close to the surface, and it's called hyporate flow, or if it is a little bit deep in the underground. Still, it's something that we can't understand. And then people excavate trenches along the isthmus because they want to see the depth at which water is flowing. But the trench is like an excavation that is very limited in space. And still, we can't connect the result from the trench to the lithology, to the soil behaviors. So there are many things that we really don't understand well. On the other hand, what we could do is very simply try to relate with a data-driven approach. There is a lot of momentum regarding machine learning. We could look at a relationship between the river flow and rainfall, the water cycle, for instance, and forget about the processes. Because what matters for engineering is the final result, is the river flow. On the other hand, once again, when you do that, you are making an approximation, something that is valid in statistical terms. This is important to be taken into account. This is another nice way of looking at links between different parts of the Earth system. Look at energy, the energy cycle, energy exchanges. It's extremely interesting. And by the way, I want to give you an example. As you know, my research activity is concentrated on floods. Usually floods are started by inspecting, modeling river flow. And river flow, depending on the rainfall, temperature. I think it could be interesting to study the energy fluxes during floods. Why? Because what makes the impact is energy. It's what we see is water, but actually the real problem is not given by water by itself, it's given by the energy associated to water, and in particular, the kinetic energy, because when the water is steady, completely steady, of course it's a problem. You get water in your house, and it's a problem because you get flooded. But if the water is not moving, it's not really a big problem. The biggest problems are originated by fast flowing water, which then takes the cars and then hits people. People cannot walk anymore. So I think it would be interesting also to look at the flux of energies during the floods. And when there is a lot of energy, one has a lot of kinetic energy that is constant. When there is only water and no kinetic energy, so there is only potential energy, it's still a problem, but less of a problem in my view. But this is something that it's not done. And I think because it is something more theoretical than looking at flow of water, which is more technical. And so I think this is the reason. Okay, and energy exchanges. Here is a more complicated diagram. It's not more complicated. It's the same diagram as before, but it is not easy to understand because there are numbers. But on the other hand, the numbers are very interesting. This is, of course, something on average over the whole of the Earth system, and therefore is, as I said, it's not representative of any location. Nowhere will you see these numbers, but on the other hand, they give an idea. And of course, these numbers are also varying in time and space, so these are averages. Anytime that I try to, I look at this diagram, I find myself a bit puzzled in understanding the numbers. So let's try to understand it together, at least for the macro numbers. So first of all, it is everything rescaled to an amount of energy that comes from the sun, which is the only flow of energy into the Earth system, that is equal to 100. Okay, so let's assume that we get 100 from the sun in a given time span, on average over the whole Earth. Okay, so first, and this is easy to be understood, we on average we have that 19% of it, so 19 is absorbed by the atmosphere, 23 is reflected by the clouds and comes back into the space. What is absorbed by the atmosphere is kept by the atmosphere. And then there is 4% that is absorbed by clouds, which means that remains in the atmosphere. And then you have 47% that reaches the surface and it's stored there. And then you have a 7% that reaches the surface but is reflected and goes back. Okay, fine. So let's concentrate now in what is absorbed by the surface. It's 47. Okay, so about half of the energy that comes from the sun. And then we may concentrate on the atmosphere later, on another sphere. But now let's concentrate over the surface. Are there other energies that reaches other energies that reach the surface? Yes, there is a 98 that was previously stored by the atmosphere, which from the atmosphere reaches the Earth's surface. And there is another 49 that is from the atmosphere released back to space. So this means that the atmosphere releases in total 98 plus 49, 147. And therefore, there must be a similar amount, the same amount coming in. Okay, but now we are focusing on the land surface. So land surface means that we have an income of 98 plus 47 is 145. Good. Now there is 116 that is emitted by the surface. And therefore, this means that we still have 29 that is in surplus. And in fact, you see that of this 29, 24 is emitted by the surface, has latent heat, like, for instance, water vapor changing to liquid or ice, and 5 is emitted as sensible heat, like raising air currents, and then you close the balance for the land surface. Now, let's look at the atmosphere. We said that we have an income of 19 plus 3 is 23, okay, and 19 absorbed by the atmosphere and 4 absorbed by clouds, okay, 23, and then we have 116 emitted by the surface. So it's 139. 139, we have 147 that is emitted, and there, of this is 104 absorbed by the atmosphere, and 12 is emitted directly to space. So what is absorbed by the atmosphere is 104 plus 19 plus 4, so it's 127. 127, and but there is also the latent heat and the sensible heat. So 127 plus 29 is 156. And then we have the outcome is 147. So it should be 9 that is emitted by clouds directly into the space. So the balance is closed. Okay. And so you see a quantification of these fluxes. Where does the greenhouse effect acts? The greenhouse effect basically should increase the amount that is emitted by the atmosphere and reducing to the land surface, reducing what is emitted to space. It can intervene in several different processes. So if you increase the greenhouse gases, you reduce, it's like a screen. So you reduce what is emitted directly to space, what is reflected by clouds, and then you increase what is emitted back. And therefore, there is an increase of the land temperature and the temperature of the atmosphere. This is another interesting way of looking again at the connections. And of course, if you want to build a model of the climate system, you have to look at all of these connections, because carbon cycle is relevant. Indeed, a huge part of climate models is the modeling the carbon cycle. You have to look at the energy exchanges, and etc. Good. So I assume that you know what is nonlinearity, but when it turns to describing these links, these fluxes, it's extremely relevant the fact that there are non-linearities. Non-linearity means tipping points. It means that a tiny change in boundary conditions, in driving forces, may originate a huge change in the final state of the system. And mathematically, non-linearity is defined in this way. Of course, you have to know this definition. You will find for sure a question, a possible question in your quiz, respective if you know what non-linearity is in mathematical terms. It's very simple. It's very simple, but still, you know, these are these two relationships. Okay, additive properties or superposition principle. I mean, this means linearity actually. Okay. This means linearity. Linearity is defined by these two conditions. If you break only one of them, it's non-linearity. Okay. Linearity means that if you make a graph between input and output, it's a straight line with different slope, whatever, but it's a straight line. So the evolution is a straight line. And linearity implies the superposition principle. You have two rains, and the resulting flood is the sum of two individual floods resulting from each rain, which is not true. We just spoke about the flood in the Romagna region. It is not true. The flood was worsened by the first one. If the first one didn't occur, the second wouldn't be the same. So linearity means superposition circle principle. And there is the multiplicative property there. This is linearity. Okay. So in your quiz, you may find like 3 possible definitions of linearity, and you have to identify the right one. Okay. And these are tipping points, examples. I think we already described them. But basically, remember, a tipping point is something like this. Let's suppose that you can describe like a relationship between two state variables of the system, and maybe annual rainfall, and let me just think if I can, yeah, okay, I think I can use this exactly because I'm just figuring out it now. And here you may have a type of vegetation or vegetation layers. Vegetation layers. This, I think, is an appropriate graph because it may describe the dependence of annual rainfall on vegetation density in a region. We know that if you change the density of vegetation, you have less evaporation, and therefore you have less water content, there are possibility changes. Like, for instance, I can give you the example of the Lake Aral disaster, which is very interesting. There is in Wikipedia a web page. The Lake Aral disaster, for it is very interesting because basically, you may have heard of it, it's a lake that is shrinking, and it's still shrinking, and but it started in 1989, I think, when the former Soviet Union, the less earlier than that, 1980, because the Soviet Union was still leaving, and they started managing the region, mainly the water, and water for irrigation because they increased the cultivation of cotton. Cotton is highly water demanding. And therefore, basically, they need water, they put water over the land. And the Aral Lake was one of the largest lakes of the earth, so it's like a sea, it's very large. And they manage the rivers much upstream, and therefore they reduced the water reaching the lake. The lake started to shrink. And then they realized that it was a problem, and but even if they tried to revert the situation, then they reduced the size of the lake and also reduced the evaporation, and therefore they registered a decrease of rainfall there. And so it's impossible to go back because even if you now remove the dams, the barrages, still there is no water into the rivers because the rainfall is decreased. So in the same time, you can, in the same way, you can describe the annual rain as depending on the vegetation density. And what may happen is that you could find a relationship that has two equilibrium states like this. And this is a classical example of tipping points, two equilibrium states. So you may have an equilibrium for a given density with a given value of annual rainfall, but then if you change the density, and you may get to a new situation where if you remove the perturbation, then you go back to the previous equilibrium. So it means that, let's suppose that you, in this case, it's an increase, which usually the human action is the opposite, it's a decrease of vegetation density. But let's suppose that there is an action that causes an increase of vegetation density. And then what happens is that the vegetation requires more water. But the rainfall is maybe not sufficient to compensate. And therefore, the vegetation dies, and then you go back to the equilibrium. This is a typical way to get a system that is under equilibrium. You perturb the system, but then the system naturally tends to get back to equilibrium, because equilibrium is the result of evolution. So for a natural system, for instance, equilibrium is the result of evolution. If you perturb it, the reaction in the system is to try to get back to the equilibrium. No, for instance, if you pollute a river with a material, the reaction of the river is to degrade the pollution by using dissolved oxygen. By decreasing the concentration of dissolved oxygen, the river gets more oxygen from the atmosphere, and that goes back to the river. So there is a use of oxygen, but then the oxygen is recovered, and then what happens is that the river tries to get back to the equilibrium. The equilibrium is clean water. But we realized when we started polluting rivers, I mean, after the first cities, people realized that the river was still okay, still clean water. But then we realized that we reached a point, the river reaches a point where suddenly there is a further degradation, which cannot be recovered. Why? Because if you get to a concentration of oxygen that is close to zero, and the river cannot compensate by absorbing more oxygen from the atmosphere because there is a limitation, this transfer of oxygen. So if there is a lot of pollution, and you get close to zero oxygen, then what happens is that some anaerobic processes start, which produce new pollutants that produce a filter that inhibits the transfer of oxygen from the atmosphere to the river, and the river gets definitely completely polluted. Same way here, if you, in a way, change your vegetation density and you cross this top, you may get to a new equilibrium with a completely different vegetation density. And this is what may happen when you turn from forest to brushes. Okay?
Legal. It's legal. They did corruption, so it was allowed for them to extract gold without passing the environmental impact, without providing the environmental impact report. Okay. The EIR assessment, environmental impact assessment. Yeah. So they were allowed to do the driving to continue this extraction without this permission. So what they did is that since they didn't do any, and they didn't have to check any guidelines, they were cleaning the gold that they extract by process of cleaning with mercurium. Okay. So this mercurium, because also they are not, nobody's controlling, they block the river flow, they block the river flow, they made a dam so that they clear this gold, and after that, they open, they left the water to go to the downstream areas, and the population were having access to that water. Thanks to this population that they are aware, they realize that that water was not clear. I don't know, maybe the information that passed, they realized that that water is not clear, so they stopped drinking that water. But I want to know, when is it possible that this technique, this water, is obvious that the water in the river wants to get into the natural state? It's contaminated. The standard is 0.01 of mercurium, they were having like 0.08. Okay. Just understand the magnitude.
Yeah.
So I want to understand if this process from to get back to the natural, is it possible to be done, or we will arrive at that point where there is this new technique, the definite new state of the river that is polluted?
In order to understand and reply to your question, we need to give an analytical relationship of the relevant card like this. And basically, based on my understanding, I think that in this case, if you stop releasing mercury, I think there is the possibility that the river goes back. Because it's true that mercury cannot be degraded, but it can be, my feeling, washed out because in a river, the river is something that is relatively easy to recover. If the mercury got in the underground, which means also groundwater, this is more problematic. And then indeed, the groundwater pollution can become a new equilibrium which cannot be resolved because there is no way to wash the groundwater reservoir. But the surface reservoir, and if the river is similar to a reservoir, it depends on the soil, on the geology of the region. If the river is like a reservoir, the river can be relatively recovered. This is what we say. We say also the laws says that with the pollution of the rivers, you have a tolerance that can be, you have an easiest solution to recover. For instance, we allow the release of water from treatment, which is good water, but not really drinkable water. So it doesn't satisfy the parameters for treatment. When you have a treatment plant, you have, but we allow in some rivers to release the water from the treatment plants. In the lakes, it's not possible. Why? Because in the lakes, how can you refresh on it? You know, so we have sewer systems in the lakes that don't have treatment plants close to the lake, or if they have that, then they cannot release water into the lake. So usually there is a sewer system that goes along the lake, and then when you get to downstream, then there is a treatment plant, and the water is released into the river. So this is my understanding of your situation, but this is a very specific problem, which I'm not an expert of. And the correct answer is be able to look at this describing the state of the system with a model. And in this case, of course, if you like vegetation, I was saying that there is generally over the lands, there are two equilibriums, brushes and tall vegetation. And in order to convert from brushes to tall vegetation, you have to make a manual intervention. You have to recover it. We say that we convert brushes to tall vegetation. And the same trees, but the same trees usually can grow up in brush form or in forms of a unique stem, a unique tall stem. But if you want to convert them, you have to manually go there and with the chisels and cut all the branches of the brush and leave only one. And until the only one is grown up, you still have to continue cutting the small branches that would form a brush. So understanding these tipping points is indeed something that is very much relevant. Here there are some examples, like Sahara, we know that now it's in equilibrium situation, it's a desert, but we know that in the past it was very green, depending on the annual rainfall. And then there was a climate change, rainfall decreased, and below a certain threshold, everything disappeared. And then there is no water there, no evaporation, and therefore that's it. It's a new equilibrium. And understanding these equilibriums, and another relevant example is the ice cap. We believe that now is an equilibrium that can be suddenly broken. We know that the Earth in the past, I mean, only a few parts of the history of the Earth has been characterized by ice caps. And this is one, because we are in the tail of a glaciation. But we also know that there is the possibility that there is a threshold, after which you don't get back. And the ice cap disappears. And I mean, probably we can survive without ice caps, but you can understand the big change in sea level elevation that would come from it. Because now the models make prediction for increase of temperature, of rise in sea level. But these predictions don't take into account tipping points, possible tipping points, because we don't know them, we don't know the threshold. So it may happen indeed that in 2060 we pass a threshold so that in 5 years we have an increase of 1 meter of sea level. May happen. Maybe that there is a threshold after which the ice cap quite suddenly melts down. So these tipping points are something concerning. On the other hand, from the point of view of engineering, you shouldn't be much concerned because, we cannot make technical design by taking into account tipping points, because otherwise we don't design anything. The unknowns in engineering usually are treated by safety factors or allowance for freeboard if you talk about hydraulics. So basically, we have to continue in this way, because otherwise, in technical design, you cannot take them into account. From a scientific point of view, it is worth continue investigating, but until we have some scientifically valid information, we cannot, in technical design, take into account the unknowns. Okay? We only have to take into account what we know. And then, when the science makes progress, then it's time to take into account the new knowledge. But this is knowledge transfer. It's from science to technology. And now, if we are working in technology, we cannot really work under the concept of a sea level rise of 1 meter in 2030. This is something that we know that it may happen, but we can't take it into account. But on the other hand, we have to continue making design projects, and therefore, this is the moral of the story. This is an interesting way of looking at tipping points in the social system. Okay, and indeed there are tipping points in the social system. Think of democracy and authoritarian government. It's a tipping point, and when you shift from one to another, it's not easy to get back. And there are two equilibriums, at least until there is a strong perturbation, like the authoritarian regime becomes self-destroying. This is something, but also the democracy can become self-destroying. And it is something that it's very interesting to look at this different equilibrium, or look now at the international economy, the free market versus now the taxes that Trump want to impose. They are two different equilibriums. And it's not easy to switch from one to another. Or, it can be easy, but you need a big change. You need the result of an election that is going in a particular direction. On the other hand, from a technical point of view, I say once again, we cannot make technical design by predicting that we may switch from a democracy to a different form of government. This is absolutely not to be done, because otherwise you don't do anything. And in engineering, this is something really to avoid. As engineers, we have to really be committed to finding solutions and making projects for solutions. Now, it's interesting to look at this diagram, but it's, social tipping is called, but we don't need to look at it in details. It's just a very nice, I think, example. Let me look at the next slides, but okay, now it's time to stop, because now we start the main part of it, after this kind of introduction. Any question? Okay, I hope you can get the concepts that I'm delivering. If you have any suggestion, if you think that you already know these things, or let me know, okay?